Hello everyone, my name is Kenny Rodriguez, ID number 2025-11-2030, and today for our MIA510A assessment number 3, I will be presenting on a suitable communication technology and protocol for our wastewater plant's remote reservoir. Looking at our objectives for this first part, it will be to assess the various communication technologies and protocols available for this type of application. Once we have selected a suitable technology, we will then compare its advantages and disadvantages and some of its features. We will then analyze appropriate communication protocols compatible to this technology, and then evaluate some of its benefits and limitations and go into a real world scenario or case study where this technology was applied. So looking into wastewater treatment plants and their reservoirs, they're normally located close to the cities that they're servicing. This keeps the pipe's length relatively short, and also you have road access. However, in between the plant and the reservoir, you do have some natural features like trees and rocks and hills and valleys that can become obstructions to any signal and can become difficult to install wired signals, or not necessarily difficult, but costly as well. Maintenance costs can also be a problem. So for these issues, we have selected or gone with wireless communication. Looking into the wireless communications that we selected to analyze, we have wireless HART, LoRaWAN, and LTE-M NB-IoT, or LTE-M or NB-IoT. So wireless HART is the easiest to implement because many instruments have it and many plants already use it. However, it is deficient in terms of the range it can reach. LoRaWAN is also another, or was also another option. It is suitable over long distances, however, the data rates or volumes are relatively small over very narrow bands or bandwidths. Finally, we decided to employ either LTE-M or NB-IoT, which can deliver relatively high volumes of data over large bandwidths, making it suitable for this application. Comparing both LTE-M and NB-IoT, we can see that LTE-M offers a higher bandwidth and full duplex capabilities. However, if there's much interference or much physical aspects blocking the signal, it can be, or the line of sight, it can be difficult for the data to reach from source to its desired receiver. Now, NB-IoT can overcome more obstacles and has a lower power consumption. And since we only plan to monitor the level of the reservoir, it doesn't require any form of control. We can rely on NB-IoT. This is a graph showing the range to data rates of these different technologies. Now, looking further into NB-IoT, it is supported by both LTE and GSM communication systems over a frequency range of 700 to 900 megahertz. Normally it operates only in half duplex, or it operates in half duplex with bandwidths of 200 kilobits per second, downlink to 20 kilobits per second uplinks, and the data volumes of 1.6 kilobytes. The technology, much like LTE-M, is for low power consumption and reliable wireless data transfers. So these devices are normally designed to last for years without changing them or doing any form of servicing. They can remain dormant, and if there's not much communication between the tower and the device, the device does go into a state of power saving. However, it's still connected to the tower, so once it boots up, it can easily connect back to the tower and share whatever data it needs to share. So looking into how NB-IoT shares its data packets, we can see that the devices normally serialize the data using any of these protocols: TLV, JSON, SNML, or CBOR. So these convert the complex data structures into serialized bits for transmission. The serialized data is packed in the application layer by protocols of TCP/IP, protocols such as MQTT, AMQP, HTTP, and COAP. These data are sent over the transport layers using either TCP or UDP. Both are reliable, however, the data packets for TCP are normally longer. They do offer some reliability or more reliability than UDP, and UDP is normally shared with or paired with COAP for its serialization. So this is a comparison between TCP and UDP. So we can see the connection setup. UDP is normally connectionless. TCP is connection oriented. So it requires some form of connection establishing before transmission. Application interface. TCP is stream based. UDP is datagram based. Retransmission is normally handled by the protocol, and UDP offers no retransmission. So the application layer, if it doesn't receive the message or it's incorrect, then that application layer has to deal with the retransmission. Data delivery, reliable in order data delivery for TCP. However, UDP is more unreliable, has no acknowledgement, so the application layer again has to deal with it. Overhead, TCP attaches its header, which is 20 bytes long. However, the UDP, as we said, is shorter. Header size is only about 8 bytes. So when we analyze the data volumes of both protocols, normally all the time TCP protocols require higher data volumes, so UDP is normally more cost effective over time. So here we see a graph of the different configurations of serialization and TCP/IP protocols that were used, and this is sort of a cost comparison based on how much data will be used per year depending on the serialization and TCP/IP protocol selected. These are some of the benefits and drawbacks of NB-IoT. So for benefits, it's extremely low power consumption. As we mentioned, it can go to a power save mode, high signal penetration, low setup and maintenance costs, I will see with the sensor later on, low data usage and cost. However, it does have some high latency, relatively low security strength. So relatively low security strength, meaning we have to ensure that we integrate some other forms of protection when sending the signal or encrypting the signal, or whenever we're sharing it in the cloud to ensure that our data is safe. Signal congestion when the network is busy can be a problem, and repeated attempts when the signal is weak can lead to failed messages, reattempts, and over time it will drain the battery. Lastly, looking at our case study, it was published by our Rusipu et al. Sorry, it's difficult to say the name. And basically, they analyzed the NB-IoT network or protocol in a similar context, but not the same. This was for a flooding management system. So they installed these sensors in what they call street storage units, just below some manhole covers. So they were able to use this sensor and measure how low they could put the sensor without losing the signal, and they found that about 0.5 meter below ground inside manhole covers still provided a good enough stable signal. This means that it can obviously overcome that obstacle, and we believe that it is a good indicator that it will be able to bypass any trees or obstructions in our application. So lastly, based on everything presented so far, we can see that we are able to employ this type of technology for our remote reservoir, and we would like to employ a Rosemount 408 wireless level sensor, which can use both LTE and NB-IoT and requires no additional setup such as any modems or repeaters or anything like that, as it can connect directly to a LTE cell tower. And it has its own cloud-based software that you can use to communicate between the sensor on your plant. This is the sensor in question. Lastly, these are our reference for these parts of the presentation. Thank you very much. Have a good day.
Hi, I'm Hayden Hebert, and I'll be discussing the DCS, or Distributed Control System for a Wastewater Treatment Plant. So today's scope is just defining what the actual requirements are for a DCS of a wastewater treatment plant. Then I will be discussing the topology selection and protocols that will be used for the wastewater treatment plant DCS. I'll be briefly talking about an example control system for a wastewater treatment plant that will be used later in the DCS performance analysis of a script that is ran in MATLAB, and then I'll be discussing the results. So the goal of a wastewater treatment plant is the removal of pollutants in a continuous recycle reactor while maintaining the pollution concentrations at the set point optimized by the SCADA system. So for control loop stability, response times are generally shorter than the sampling times, and they require predictable transmission, minimal latency, and jitter. The control and safety data require high reliability and strict real-time constraints, with diagnostic and historic data placing less emphasis on reliability and real-time constraints. So a DCS is really just a distributed network of medium to complex control systems. So specific to our problem for a wastewater treatment plant, and pretty much in general of DCSs, but for a wastewater treatment plant, these are generally going to be control loops that are not as well, essentially the time constants of the processes involved are not super strict. It's not going to be like robotics, so there's going to be a lot less emphasis on real-time performance requirements. But in general, we want a scalable solution that uses open standards so we're not vendor locked and we have more options, thus cheaper products. We want it to be redundant. Obviously, we do not want a municipality losing treated wastewater. And then we also want performance at a reasonable cost and commissioning time. So what we went with was DLR ring, Ethernet IP, and HART on 420. I also in the script used PTP and Ethernet on CIP for just the uh, simulation of the network topology. But so the reason why we went with DLR is it's redundant and has very fast fault detection and recovery, and this contrasts to STAR, which has single point failure, lots of cabling, bus where one cable fault breaks every upstream node, or mesh, which isn't practical at the device level and is expensive. So the DLR ring tolerates a single cable or node break, and by virtue of having every mode with nodes, excuse me, with a two-port switch, the topology uses less standalone switches and less cabling than the Star. So the recovery for DLR is about 3 milliseconds for a 50 node ring with a default of 400 microseconds beacon interval, which is very well within range for a wastewater treatment plant. So at the control level, we use Ethernet IP. It's very common in the industry, and it has the benefits of having the Internet protocol suite with TCP or UDP. So it offers deterministic, cyclical, and implicit messaging over UDP specifically for implicit messaging with fixed packet rate, which is beneficial. So um, we also use HART on 420. So all these standards, the three that I mentioned, the DLR ring, Ethernet IP, HART on 420, they're all open standards, which, as previously mentioned, is a beneficial factor in selection because open standards generally are not vendor locked, and open tooling, which is very nice to have, So further on, hard on 420. So it's backward compatible with all 420 analog measurements. And so we still get most diagnostic tools and uh, most diagnostic tooling as seen in others like digital multi-drop buses, but hard on 420 actually doesn't require a bus-powered segmented design with additional bus infrastructure. So this is going to be less commissioning effort. So this is just a general showcase of the um, wastewater treatment plant at Califat by D. Selitz Anu. I definitely pronounced that wrong. But so this is just what I'll be using as a basis for figuring out frame data and payloads. Um, so yeah, so there's 4 general loops and uh, multiples for 2 of them. So for the actual simulation of the network, just for general bandwidth and um, hardware requirements. So the way it works is I simulated the example control loops of the Califat wastewater treatment plant with 3 DLR rings. So realistically, all these control loops should probably be inside one ring, but uh, an earlier design choice made it so we chose 3 DLR rings. But anyways, the MATLAB code showcases the choices were well within limit. Obviously, when you actually get into the actual plant and you have more, say, auxiliary systems on the actual rings, then the performance will become more constrained. But as a general showcase and baseline, the results show that we are well within the performance needs of a wastewater treatment plant. So each ring was modeled to have the device's cyclic I/O frame from its CIP, Ethernet and IP/UDP headers with the HARP payload, and tagging the PTP stream as COS7, which just means it's going to be higher priority than the tagging of IO, which was tagged at 5. So the script evaluates 3 limits: bandwidth floor, where the link carries some bits per RPI of every stream; the worst case latency by combining the store and forward switch fabric and propagation time with CAN style response time analysis for queuing delay. So also we saw busy period with fixed point iteration checked against the RPI and Ethernet IP connection time, and yada yada yada. We also use bisection, but I'll just get on to the results rather than further talk about the analysis. So, um, so these the top are the 3 rings simulated for the minimum link rate across the RPI, and this RPI was dictated by um, the the protocol used at the field level. So with the process required RPI of 0.5 seconds, which was taken from the polling rate of heart, as shown with the red point there, all 3 rings were well within the link rate demand, and they only required a demand of 0.01 megabits per second, which was super low. So as mentioned, as we further expand more systems onto the rings, this will become, it will require more link rate, but like this will not be a super demanding result. So in the bottom, so on the left, so pretty much I swept for the minimum sustainable RPI, and the results were all far below the required RPI, which is shown in the horizontal red line. So the link rate was spanned for 2 megabits per second to 1 gigabits per second for the minimum sustainable RPI. And again, this just shows that everything is well within range. And for the bottom right, where the reference switch was 5.2 microseconds, this becomes more of a demand constraint. But still, that the switch latency only becomes binding at sub-milliseconds RPI. So from these results, I'm postulating that as the expansion of the nodes increases, requiring more switching due to hops, that the DLR ring recovery time becomes more of the driving constraint, which would also drive the switch constraint as shown in the bottom right. But again, this is not anything that would warrant the use of super high-end hardware, but it is more of the constraint I am willing to believe that the network design engineer should model thoroughly before choosing actual hardware once you actually get more of the plant requirements and all the time constants for the process dynamics where you can actually model everything as a cyber physical system and then uh, yeah, and then you can actually get some actual simulations going with um, more node hops and then more constraints with protocols and priorities and all that. But yeah, so these are the references I had, and thank you for your time.
Hello, and welcome to Part 3 of Assessment 3, Designing a Suitable Communication System to Connect the DCS Equipment Within a Wastewater Treatment Plant. My name is Michael Stafford, and I will present on the hardware resources required for the internal DCS network. Our objectives for this portion of the presentation are to provide an overview of the plant DCS network, to provide details of the network physical layer, to provide details of the controller, I/O, and switch specifications, to provide details of the HMI, and finally, to provide details of the noise and mitigation strategies we will use. Figure 1 shows the various layers involved in our DCS architecture. Level 0 is the field instrumentation. Level 1 is the PLC control network. Level 2 is the SCADA DMZ level. And level 3 is the enterprise level, which consists of the corporate IT and IIoT cloud, which is collecting data from our reservoir level transmitter. Diving deeper, level 0 field instrumentation physical layer will include the following. Wiring for instruments will be armored, shielded twisted pair. Instruments will be heart capable. Wiring for discrete devices will be armored multi-conductor cable. Wiring for motor control in the MCCs will be shielded Cat6 with the metal jacket connected to the switch. Additionally, instrumentation will be Anderson-Hauser where possible, as Rockwell and Anderson-Hauser have a partnership which allows Anderson-Hauser instruments to be configured directly in Studio 5000 and reduce the need for an instrument technician to go to the field for initial troubleshooting. Motor control will be Rockwell PowerFlex VFDs, E300 electronic overload relays, and SMC Flex soft starters. All are Ethernet IP devices and can be configured directly in Studio 5000. Level 1, our PLC network physical layer, will include the following. Wiring for PLCs and I/O will be shielded Cat6 with the metal jacket connected at the switch. If required, due to distance, cabling will be armored fiber optic with termination in local switches and shielded Cat6 from the switch to the I/O rack. And it will include redundant device level ring as the network path. Level 2, our SCADA DMZ physical layer, will include the following. The wiring will be a combination of fiber optic and Cat6 as required by length. Switches will have redundancy. Firewalls will be placed between the SCADA server and PLC network, between the SCADA server and DMZ, and between the DMZ and corporate IT/IIoT cloud layers. Layer 3 enterprise physical layer will include the following. The wiring will be a combination of fiber optic and Cat6 as required by length. And a firewall will be placed between the DMZ and corporate IT/IIoT cloud. Our hardware overview of the PLC, I/O, and switch selection. Rockwell PLC rack will include ControlLogix 5580 family with redundant processor, part number 1756-L83E. This processor includes the following features: a maximum of 250 Ethernet IP nodes, 10 megabytes of memory, a built-in Ethernet IP port. This rack will also include multiple Ethernet IP dual RJ45 port cards, part number 1756-EN2TR. The choice of this processor allows us to expand our network with additional Ethernet IP nodes. Ethernet IP nodes include inter-PLC communications as well as all other Ethernet IP-enabled devices, such as VFDs, soft starters, and electronic overload relays. Multiple EN2TR cards will be utilized to properly segregate I/O cards from motor control equipment and inter-PLC communications, creating separate networks with single types of data transfer. Our I/O will be Rockwell Remote I/O with Flex 5000 family, which includes Ethernet IP adapter with dual RJ45 ports, analog HART input cards, analog HART output cards, DC digital input cards, DC digital output cards. And Flex 5000 analog HART cards utilize HIH, which is high integrity HART. This allows some basic configuration to be done at the I/O tree level in Studio 5000. The Rockwell switches will include Stratix 8300, which will be placed in level 2 between the SCADA and the DMZ, Stratix 5400 between level 2 and level 1, and Stratix 5410 will be utilized for the device level ring network for the field devices and remote I/O. DCHP will be enabled on the device level ring of the field equipment, and static IP address is assigned to each port. This minimizes the amount of field setup required for VFDs, soft starters, and electronic overload relays, and reduces the chance for error in initial startup. Plant Packs is Rockwell's DCS offering and consists of several workstations and servers. The following installations are on the OT network. Engineering workstations would utilize Studio 5000 to configure PLCs and available Ethernet IP devices, as well as using FactoryTalk View Studio for configuring HMI graphics. Operator workstations, which operators utilize to control the process. FactoryTalk Directory is a standalone server that also hosts the FactoryTalk Activation Server. The Process Automation Server, otherwise known as PAS, hosts FactoryTalk SE, Data Server, and Alarm and Event Service. FactoryTalk Historian is a standalone server that is used to provide trends on the HMI faceplates. FactoryTalk Asset Center is a standalone server. The following installations are placed on the DMZ. ThingWorks, which is used for connecting IIoT devices to plant packs, and Aviva Pi Historian, which is long-term data storage and serves data to the enterprise layer for use with other applications. Noise and interference mitigation will be achieved by the following. Use of armored, shielded, twisted pair for analog instrumentation. Use of multi-conductor cabling for discrete devices. Use of shielded Cat6 cabling for Ethernet IP devices. Adhering to proper shield grounding principles of terminating only at the PLC and network switch end of cables. And the use of fiber optic cables for long runs. References for Part 3 of this presentation are white papers, selection guides, technical data, and module specifications from Rockwell Automation. This concludes our group presentation for Assessment 3. Thank you.